Hi again. Today we're going to talk about the universal wave equation. Okay, just a simple formula that we're going to build to here. I've drawn a transverse wave. It's got, say, 2 cycles in there. I'm going to introduce this wavelength. This is the Greek letter called lambda. Okay, so it's not my failed attempt at a 2. That is a Greek letter. Okay, and that's the distance a wave travels before it repeats itself. Okay. So if I've drawn a wave, this is kind of maybe we're watching a wave go by. A wavelength will be the distance between troughs, which again, a trough is the bottom of a wave, or the distance between crests, which is the top of a wave. That's the easiest way to recognize a wavelength. If you pick somewhere in between, you got to go through the line once, because it's not repeating itself here, because here it's at this point but going down. Here it's going up, so it repeats itself here. It's going back down. So an easy way of just labeling a wavelength on a transverse wave is it's the distance between crests or troughs. Okay? So again, that's how far the wave travels before it repeats. The time it takes to travel that distance, well, that's the definition of period. Remember, period is the time for a complete cycle. All right? Now check this out. I'm hiding this, sorry, but all the logos there. So speed is just distance divided by time. If we make the distance equal to a wavelength, the time it takes to travel a wavelength is a period. So we can get that the speed of a wave is equal to the wavelength divided by the period. We can also introduce frequency again. Frequency is 1 over period. So you can see the speed of a wave is wavelength times frequency. This is the universal wave equation. Okay, and we're usually going to use this form. All right. Some other things just know. When a wave enters a new medium, so maybe that's going from air to water or water to air, the wavelength of that wave changes, but its frequency typically doesn't. But since the speed of a wave is equal to frequency times wavelength, if the wavelength changes, frequency doesn't, the speed will change. Okay, so the speed of a wave changes in different media. Whatever it's traveling through will affect its speed. All right, so I'm going to set up this example, a bit of local flavor here. Moose FM, it broadcasts radio signals at 100.1 megahertz. Okay, FM, if you didn't know, stands for frequency modulation. So those numbers, I don't know if anybody uses a radio anymore, maybe in your car. The number that shows on the dial is the frequency of radio signals that they are producing from their tower. Okay, radio signals are a type of EMR, which means electromagnetic radiation. They travel the speed of light. Okay, so that's the speed of radio signals. This is its frequency. We are going to be able to find the wavelength of Moose FM's signal. All right, it's going to be easy. So speed, 3 times 10 to the 8. Wavelength's what we're looking for. So this is frequency. This capital M means mega. On your formula sheet, if you forget, it has all the metric prefix symbols and what they mean. Mega means million. That's 10 to the 6. Okay, so the frequency of the waves that Moose FM is producing is 100.1 million hertz. So it completes 100.1 million cycles every single second, which is pretty cool. All right, let's see what we get when we divide. So I get about 3. I get 2.997. Let's write it like that. This is a length. Wavelength is a length. That's meters. Okay, so this is just good to know in your day-to-day life. Radio signals have a very high wavelength. All right, they travel through your body, through buildings, without really disturbing anything. If you have a lower wavelength signal, all radiation travels the same speed. If you have a lower wavelength, that means you have a higher frequency. Higher frequency radiation is more damaging. Radio is actually the safest. It travels through your body, like I said, without really affecting you in any way. All right. There's a whole spectrum of radiation. The highest frequency radiation is gamma. Okay. Gamma rays will actually mess with your chromosomes. Okay. They have a tiny wavelength and they will interact with your physiology and cause things like tumors. All right. Other types of high frequency radiation are ultraviolet, which we know aren't so good for your skin. They cook you. Between ultraviolet and gamma rays are X-rays, which travel through our skin but bounce off bones. If you've ever had an X-ray done, say at the dentist, they put a lead apron on you to protect your organs and then leave the room, which suggests to me that they're not totally safe. All right. In limited exposures, X-rays are very useful, as you're aware. All right, another type of radiation I just want to talk about briefly. This is all physics 30 stuff. You absolutely don't need to know this, but I like people to know it. A microwave radiation, which, as the name suggests, is what heats up food in a microwave, is kind of unusual in that it's fairly low frequency, lower than visible light. The reason it heats up food is because it excites water molecules. All right, so the wavelength of the microwave radiation is roughly the same length as the bonds in water. Okay, so microwaves can heat up water. If you have something totally dry in the microwave with absolutely no water, it won't heat up. And the inside of a microwave isn't really hot. It's just water inside that will get hot. All right, so again, microwaves are damaging to our physiology, but not because of the high frequency, just because we're mostly made of water. I hope that's interesting to you.